Hello and good evening, Devs Connect. My name's Ruhi. I'm a software engineer at a company called Smart Numbers. That's probably already too much information about me for you to remember, so I'll skip my life story this time. What I do want to talk about is a technique called property-based testing. Now, if you're not already familiar with this technique, I imagine your first question is going to be, what's property-based testing? I think the best way to answer that question is to just show you through an example. So sit back, relax, and enjoy the ride. Of course, to talk about testing, we are going to need some code to test. So let's suppose we have the following problem. Now don't worry, this isn't an interview, you're not in a test, but it would be useful if you think about how you'd approach this problem. I'll read it aloud, thanks to Hillel Wayne for the example. For a given list of integers, return the maximum possible product of two elements in the list. Here's some Python code you might plausibly write to solve this. It's probably a lot for this time of the night, so we'll take it line by line. We have a function called maxprod, which takes a list of integers as input and returns an integer. The first thing we do is we check that we have at least two elements in the list and throw an error if we don't. A nice bit of defensive programming. Getting to the real meat of the function, we sort the list, take the largest two elements, and return their product. This seemed like a reasonable implementation to me. I imagine some of you will have already spotted the bug at this point, but don't worry if you haven't. Let's just think about how we test this function. Test 1, we have the simple list 1, 2, 5, and assert that the maximum product in this case should be 2 times 5, which is 10. Test 2, mixing it up now, the maximum product in this case is 5 times 3, which is 15. Test 3, we assert that when the list doesn't have enough elements, we throw the error we expect. I'm sure we're all familiar with writing tests in this style. They're what I'm going to call example-based tests, because we choose particular examples of inputs and assert that we get the correct output. But suppose it was time to push this code to production, so to speak. Would you be satisfied that the code is correct from this test suite? Before we answer that question, let's just take a detour and think about what it means to test a function. So we have a function which takes lists of integers as input. You can imagine there being a set or space of possible inputs to this function. So every dot behind me represents a different list that we could use. With example-based testing, the idea is that we choose a few inputs from this space, assert that our function works for those, and hopefully that gives us confidence that the function works for any input in the space. But if we just highlight the inputs that we have tested, I think there's an obvious shortcoming here. We barely cover any of the input space. What that means is there are massive regions which are essentially untested where bugs could be lurking. Of course, there are ways to combat this. We could write more example-based tests, but there are two issues with that. One is, quite frankly, it gets a bit tedious, and two, it's not obvious how you write examples or how you choose examples which exercise your function in meaningful ways. This motivates the first idea of the night, which is why don't we get the computer to randomly generate inputs for us? If we offload that work, we can cover a large chunk of the input space automatically. Let's think about that idea for a bit. What would a test look like if the input was randomly generated? Now, I'm going to be using a Python library called Hypothesis for these code examples, but that's not really important. It's just the idea I'm trying to get across. First, we tell the library what are the inputs to our function. Here, we generate random lists of integers and which have a minimum size of 2, because we just want to test the happy path for now. We get to writing the test body and we run into a hitch almost immediately. With an example-based test, it's easy to assert what we should get from maxprod because we manually work out the correct answer. But what do we know about the output if the input is randomly generated? Let's just think about that. I think this idea can still work, but we need to take a step back and think about what it means for our function to be correct. Suppose we have a random list. Here it's just 5, 1, 3, 2. If we want to work out the maximum product of this list, well, by definition, it's literally the largest product when we take all the products. So what we could do is take all the pairs of elements, work out their products, and pick the largest of those. And if you think about those steps, there's nothing there that really depended on the exact list that we started with. What that means for us is that we could actually encode those steps as a test. So let's take this test again. We generate random lists of integers with a minimum size of 2. We generate all the pairs of elements from the list. We work out their products, and we assert the result of our function is bigger than all of those products. And that's it. That's a real executable test. So when we run it, we find that, oh, our test failed. Once you get over the momentary shock of being told your code is incorrect, you can see that the library's provided a falsifying example for us. In this case, -1, -1, 0. And you think, oh, of course, we didn't think about negative numbers when we wrote our code. For this list, the real maximum product would be -1 times -1, which is 1. But our bugly implementation would have given us 0 times -1, which is 0. Good thing we had to test to catch the bug. Let's just recap for a second. What have we done so far? We had a problem, and we thought about how we might test it using traditional example-based tests. A shortcoming there is that we tend to not exercise much of the input space, which means that bugs can be lurking for inputs we haven't tested. That motivated the idea of getting the computer to generate test inputs for us, meaning that we now think about correctness not in terms of specific examples, but of properties we expect to be true for all outputs of our function. Now, know what you're thinking. Okay, this was nice on your toy example, but how do you really apply this in the real world? And that's a fair criticism. This was a toy example. But now that we're familiar with the technique, why don't we go through another example with a bit more complexity, which might show you how you can use this in your day-to-day work. Sticking with the theme of interview-style questions, let's talk about binary search trees. Thanks to John Hughes for this example. So suppose we have a binary search tree which stores key-value pairs. There are 3 methods on this interface. The first is the insert method, which takes a tree, a key, and a value, and returns a new tree with that key-value pair inserted. We then have what's essentially the opposite method, delete, which takes a tree and a key and removes the appropriate key-value pair from the tree. And finally, we have a find method, which takes a tree and a key and returns the value associated with the key in that tree. I probably don't need to spell out what example-based tests for these methods would look like. For an insert method, for example, you might handcraft a tree, insert a key-value pair into it, and then compare that with what you expect the output to be, again, handcrafted. And I want to be clear here, I'm not against example-based tests. They're absolutely a useful tool to have in your toolbox. Having said that, I do think it's useful to think about what a property-based test might look like here. So, suppose we want to test the find method. We generate a random tree and a random key. That's the easy part. And again, we run into a hitch when we want to write the test body. What does find return for a random tree and a random key? Either the key is in the tree and we want to return the associated value, or the key isn't in the tree and there's nothing to return. But how do we know what case we're in? Well, with a bit of creativity, you don't need to know what case you're in for a random tree. You can instead construct a tree for the case you want to test. What I mean by that is if we want to test the case where the key value pair is in the tree, we'll take your random tree, insert the key value pair into it, and now you know if you call find on that new tree with that key, you should get the value you expected. Likewise, if we want to test the case where the key definitely isn't in the tree, we take our random tree, we call delete on it, so either the key was already not in the tree or we've now removed it, and when we call find on the tree without the key, there should be nothing there. With that, we've come to the end of our 10 minutes, so That was a taste of property-based testing. Of course, there are many more things that could be said here, but hopefully that gives you an idea. Thank you for listening. My name's Ruhi. If you go to my website, ruhi.dev, you should find an accompanying article for this talk where we go a bit deeper, hopefully in the next couple of weeks. But thank you for listening, and I'd now like to open the floor to any questions.